Today we are going to get into our X-ray lab, which is investigating material structure using X-ray diffraction, and we're going to look at kind of three basically sections of this lab. So first we're going to look at the structure of metals, and the metals that we're going to look at are copper, which is FCC. We're going to look at chromium, which is BCC. So we're going to look at the structure of metals, how we should expect those to appear on our basically XRD plots, which we know from class. Metals have long-range orientational order, so we should expect something kind of like this, where we see, again, this kind of nice crystalline structure, purely 100% crystalline, no amorphous regions in metals. So we'll either see basically peaks where we won't. So similar to our RDF and PDF functions, this G of R, R, for metals, we kind of see the similar kind of pattern from our PDFs and our X-ray diffraction plots as well. Then we're going to get into polymers. Now, polymers are basically semi-crystalline material, or they can be amorphous materials. The main thing is that they're never 100% crystalline. So no polymer is ever 100% crystalline. So we are going to look at polyethylene oxide, or PEG. Glycol, this is a semi-crystalline polymer. Semi-crystalline. And then, that would be different from our PMMA, which is a fully amorphous polymer. So for PMMA, I'm going to kind of color this green or blue, we should expect something a little bit different in terms of our 2 theta plot. So I would expect, if it's fully amorphous, again, no semi-crystalline regions, so no long-range order, so just a few peaks to see here. But in comparison to PEG, which is semi-crystalline, you might see kind of some sharper peaks. Again, not as sharp and not as kind of as the kind of delta function that you see for polymers, but you'll see more kind of peaks occur here for semi-crystalline regions. Why? Again, this has long-range orientational or long-range translational order. PMMA does not. So it will only basically have short-range order. So that's kind of the first 2 chunks. And again, we're going to kind of measure some parameters that we're going to go through in a second. Structure factors for metals. The polymers is more of a qualitative graph. And then finally, we're going to end our discussion with this case study of lead titanate and the polymorphic transition. So polymorph is, again, this material that can exist in multiple structures. So specifically here, tetragonal to cubic. Iron also does. Iron is a polymorph. It goes from FCC to BCC. But anyways, we're going to get into that a little bit later. We'll see how temperature changes that structure and then what can kind of occur there. So let's get into kind of, again, some of the background and theory. We know from our basically previous discussion in class about Bragg that we need for Bragg diffraction the series of regular space obstacles that need to be comparable to the magnitude of the wavelength of the incident beam, and then we need to have this constructive interference. So we are going to use in this lab copper alpha radiation. So our lambda is going to be 1.54 angstroms, and again, that meets our condition, right? Because that's the length scale that we're looking at to kind of investigate in the structures that we're looking at. So hopefully everyone remembers, and we're going to look through some slides too in a bit from our X-ray diffraction. We have our Bragg's law here. And again, remember, this is different from our graph here is 2 theta from our X-ray diffraction. So we can, from these angles, from this wavelength, we can kind of figure out and start to deduce when we see a peak, that's going to occur at a certain 2 theta angle. And then for that peak, we could kind of figure out, okay, what is that interplanar spacing? Or more general for polymers, just what is this D, this kind of characteristic length. So characteristic length. So we can also relate this kind of interplanar spacing for cubic materials. So we have this relationship for cubic materials. Again, for our metals, this only holds for kind of interplanar spacing, this DHKL. That is for metallic materials, not for polymers necessarily. You could also do something similar, but that's beyond the scope of this course. So luckily, we don't have any hexagonal materials or tetragonal materials except for lead titanate, but you kind of see there's other relationships if you're orthombic, tetragonal, hexagonal, monoclinic, and it gets a little bit kind of more complicated. So one of the questions, Bragg's law tells us when we're going to get the conditions necessary for diffraction, but it doesn't tell us about relative peak intensities, and then it doesn't tell us necessarily about when, what interplanar distances, what HKL indices, when should we expect to kind of see a peak, or what's the amplitude or the intensity of each of these kind of peaks. And when I'm talking about peaks, I'm talking about peaks in our 2 theta. So when do we see peaks? That's governed by this law. And lambda equals 2D L sine theta. But how do we determine the magnitude of this peak, height? And what HKL indices, what HKL indices does each peak correspond to? So that's going to be answered by the structure factor, F. The structure factor is very, very important, and it's actually a beautiful kind of, again, the full derivation is a little bit beyond kind of the scope of this lab, but it's a beautiful kind of framework, an algorithm that's going to allow us to tell when do we expect to kind of see peaks. So in this equation, n is the total number of atoms in the conventional unit cell. F sub n is the scattering factor of the type of atom. Now, sometimes, for example, brass. Brass is basically an alloy. We're going to learn about that pretty soon in class. It's made of copper and zinc. So you can have some structures that have multiple kind of atoms, but and actually you could get some really, really cool kind of structures. Zinc blends, NaCl, these kind of type of ionic structures. It's really kind of, you get this kind of inner lattice, or actually superlattices, superlattice structures. So superlattice structures are kind of a really cool thing. If you take a higher level and a graduate version of my course, you might kind of do this lab. But anyways, it's a little beyond the scope of our class. So luckily, we're usually only dealing with one type of atom. So N is just going to be either copper or chromium. So let's go ahead. Again, it's going to be a function of this Bragg angle as well. So the structure factor, that little f, also varies as a function of that Bragg angle. But anyways, that's a little bit beyond the scope of this class. But let's go back and let's kind of look and figure out, what does the structure factor tell us, and what intensities should we see as a function of these HKL indices for a BCC structure. So what is the n total number of atoms in a BCC structure? 2. We've done that in class. What about FCC? Well, our n is equal to 4. Now, if BCC has 2 atoms per cell, we could pick, again, look at BCC structure. So like this. I've gotten fast at these over the years. So I can pick any 2 atoms in the structure, but I'm going to be strategic. So I'm going to select these 2 atoms. These are going to be my basis set of atoms in this kind of cell. So let's go ahead and plug that into this equation above here. So let me kind of strategically put it. So my structure factor HKL is going to equal the sum of, and again, F of chromium times, and let's just kind of do this expression. So what's the position of the first atom? 0, 0, 0. So I know it's going to be, what is e to the exponential of minus 2 pi I times 0? Well, it's going to be 0. And what's e to the 0? Well, let's pull up Mathematica in case we haven't. Again, spending my time on this. Is this really a worthwhile exercise? Yes, because it's always good to kind of look at your math before you kind of publish your results. So let's go ahead. Let's do it. Exponential times minus 2 times pi times I times 0. And what do you know, it's going to give us 1. So we've got to flip our little book back. That's going to give us 1. And now the other atom, though, that's going to lead us to this. So this is going to be exponential of minus, I'm going to do kind of some, again, because we're plugging in for the x coordinates, right? So we're plugging in the coordinates here. So that's why it was 0 for the last one. But for here, we're going to get minus, excuse me, let me erase a little right there. Actually, I'm going to erase here too, just to give us some little bit of room. Superlattices, it'll come back in another video. Minus pi I times h plus k plus l. So this is kind of our function. This is our structure factor equation for BCC structures. And again, I'm just taking that half out because, again, I'm just plugging in a half. So let's figure out what are the conditions for H, K, and L that will allow me to see a signal. Well, what happens if, for example, H plus K plus L is equal to an odd number, for example? So let's say I pick 1, 1, 1. So let's see what's going to happen if I plug in 1, 1, 1. So what does that equal here? So I know that this is always going to be a positive 1. But if I go to e to the minus, so if it is 1, 1, 1, that's going to be e to the minus 3. People remember their Euler's relationship, but again, it's easy to know. Let's just plug it into Mathematica just to be safe. So, excuse me, minus pi I. So if it's 3, it's going to be -1. So if it's -1 here, 1 plus -1 is going to cancel out. So I'm not going to see a signal. So for 111, no signal. What if h plus k plus l, what if h plus k plus l is equal to even? So for example, 1, 0, 1. That would be 2. So if I add those together, what if this is 2? Oh, it's 1. What if this is 4? Okay, what if this is 1? So if it's odd, it's not going to work. But if it's even, we are going to get a positive 1, and we're going to get a signal. And you can kind of see going through here, that's going to be our selection rule. H plus k plus L must be even. If it's odd, do not see a signal. And then we could also get to the intensity is just going to be this square. So FCC, you can look in the kind of analysis video, we're going to do the same thing. So you're going to be asked in this lab, we need to figure out what are the structure factors. So I need to know what are the rules, the selection rules for each metal. I also need to know for the first peak, we're going to only analyze the first peak of our metals here. I want to know for the first peak, what is my DHKL? What DHKL does that correspond to? What is my A? That's another thing I want you to kind of figure out and show me. I also want to know what is the crystallite size. So one of the kind of cool equations that you could utilize, again, is kind of beyond the scope of this course, is the Schur formula. So we can calculate, actually you could also calculate percent crystallinity as well, but we could calculate the average crystallite size by using the Schur formula here, where lambda, we already have that, we already know what the Bragg angle is, and then B is this value of full width of half maximum. So in each of those kind of peaks, it's not just a delta function, there's a little bit of width to it. So the full width of half maximum is what is the length? This is the B. The full width in, B is going to be in degrees, angles, an angle. What is the full width of half maximum of our intensity peak? So you're going to do that for the first peak that you see in your X-ray diffraction plot for the metals. So be sure to do that, and again, you can look at kind of the example that come along with it. And finally, we are going to do a case study of lead titanate. The lead titanate is a very, very interesting material. It is a polymorph. So polymorph is, again, carbon and iron are polymorphs. So carbon can be graphite. So carbon can be in kind of multiple structures. So carbon can be a diamond structure. It can also be, carbon can be graphite. Actually, even a single sheet would be graphene. But anyways, iron too. Iron can exist as BCC or FCC as well. So they could contain multiple kind of different structures. Lead titanate is a very, very interesting structure. It's called a perovskite. And actually, let's go ahead and look at kind of the formula, or actually what's going on with lead titanate below here. So this is just the attached kind of X-ray diffractions of constructive interference, destructive interference, looking at copper alpha radiation, again, general form of Bragg's law. Again, you can kind of look through this at your leisure. We're going to be looking at those interplanar distances. You can kind of look at the planes and kind of hopefully start practicing for your problem set. Again, this is from a lot of it from Geetha Barrera. Radial distribution functions. Again, we're going to talk about that a lot in class. And hopefully you watched that video already. And here you can kind of already start to see, right? For PDF, again, gas, crystalline solids, you see the peaks, the wider peaks for amorphous solids or semi-crystalline. And here you could also see the difference between amorphous versus crystalline, again, for, actually, let's go ahead and change the color here. So purple. So this, as you hopefully can see, this is going to be my amorphous. And you can see here it's A versus C. And my crystalline will be this here. You see kind of these more peaks, sharper peaks. Again, there's these long-range orientational order compared to kind of, again, the broader, strokes essentially of, again, there's more long-range translational order in your crystalline regions. So you have sharper peaks and more of those peaks that extend in longer distances. Structure factor, again, we've kind of went through that nice derivation here. A really cool part, if you, we're not going to unfortunately do that in this lab again for another course. You could actually calculate the percent crystallinity of polymers. So you could do that. Most XRD programs have this built in. So you could break down these peaks and look at basically the area of these peaks. Again, these are broad peaks, but there's some amorphous contribution, there's some crystalline contribution, and then you can kind of just look at some of the area on the crystalline peaks versus the total area to get the degree of. But so PMMA, again, this is amorphous, this is semi-crystalline, very important when you talk about that in this lab report. But here's lead titanate. So above, so we have basically lead titanate structure. So let's go ahead and do a plot. Actually, let's do the volume versus temperature. And there's this magic number called TC. It's like the Curie temperature, not the Curie temperature, this kind of transition temperature. So if we're above TC, the structure or our volume is pretty low, right? Because we are below above TC, we are cubic, as you can kind of see here, essentially. And this is called a perovskite structure. So perovskite. So below, when we're at this cubic, well, actually, we'll get into the properties in a second, but when we're below TC, this volume increases. So, and we are tetragonal. So this is already an interesting material because basically what we're saying that the change in volume as we increase temperature, dV dt, is less than 0. Most materials are greater than 0. So this is a unique material. It is a negative thermal expansion coefficient material. So as you increase temperature, it actually shrinks. Again, you go from this tetragonal to this cubic structure here. But there's also, again, structure dictates properties in this class, right? You can also see this titanium atom, it is kind of offset now from the center of the cell. And this creates kind of unique electrical, optical, and even magnetic properties. You create this kind of polarization. So this charge, this +4, is not balanced out by these kind of surrounding. It's basically, this is called a let's see, 1, 2, 3, 4, 5, 6. It'll be a tetrahedral. I believe it's a tetrahedral site. So actually, let's go ahead. It's a tetrahedral. I think it's an octahedral. So let's look at this one. It's an octahedral site. Yes, this is an octahedral site. Excuse me, not tetrahedral. Tetrahedral would be a little bit different. So let's see, octahedral sites versus tetrahedral. So it's all about the number of atoms that are kind of surrounding it. So let's look for a good diagram here. Octahedral sites, again, they're going to have 6. That tetrahedral hole is going to have 4. So just the numbers of that kind of the nearest neighbor. I need to refresh myself on this memory. So anyways, when it's offset from that kind of octahedral site, it creates this polarization vector. But you can see as temperature increases, when we shift to this kind of cubic material, we're balanced, right? So we lose, basically, your P is equal to 0. You lose kind of these unique kind of electrical properties. So that's kind of, again, the beauty of this lab. And, again, structure dictates properties. When we switch from tetragonal to cubic, we lose these electrical properties because now that titanium atom is not offset. I look forward to your discussion of that in our kind of lab. And so we can see kind of a lot of these kind of different structures pop up. So here we can see that if we go back to our, there's a certain temperature. Let's go all the way back to our perovskite. So the Curie temperature, that T sub C, equals to 490 degrees C. So we know that above the Curie temperature, we should be cubic. So here, this is 400. So we should be tetragonal. So this kind of this is basically your kind of international crystallographic database where should we see peaks. So this would be if our structure is tetragonal. This would be if we're cubic. You can see here we have kind of 2 peaks for tetragonal. We have 1 peak for cubic here. So again, our TC is equal to 490 degrees C. We know that when we're below TC, we are tetragonal. When temperature is, when TC is greater than our temperature, or let's just do, when temperature is less than TC, we are tetragonal. Temperature is greater than TC, we are cubic. So we should be tetragonal here and here. And you can see the 2 peaks, right? Peak, 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 peak. But then at 800 at 530C, we can see here a single peak. So you could see from X-ray diffraction, as we increase temperature, you see that shift, right? One peak, we go to the cubic. And then again, at room temperature, 2 peaks tetragonal. So you can kind of see this transition. Actually, you could see it morph basically you can kind of see these lines cooled back down, heated up, and you can see where these peaks occur. And you can see the shift, right? So 2 peaks, so again, at low temperatures, and then as we increase temperature, it starts to merge into a single peak when you come cubic. That is a discussion that, and you can see a different form of this as well. So remember, 2 peaks, 1 peak. Be sure to kind of include that. That's kind of the last part of the discussion in this lab. So discuss that, and you can kind of start to see we can now. That's kind of what's expected in this lab. So be sure to kind of do all those things again. Thank our amazing kind of instructors who inspired this lab. Really appreciating Dr. Geeta Barrera. That kind of really kind of did the help in developing this lab. Also, one of our EOP students that helped kind of write in the procedures for this specific X-ray diffraction device. And now we're going to go into actually running the experiment. So all these materials and methods and these details, you're going to kind of see it in person as best as possible with this kind of status of remote teaching. So excellent. So I'll see you in the lab, and then we'll come back and we'll do some data analysis, and then you'll be off and running and writing a lab report, reading, or not lab journal articles. So I will see you then. Thanks.